Welcome back. So in our last lecture we talked about carrier transport phenomena, and especially we talked about drift phenomena in semiconductors. We concluded our discussion with an exercise problem. In this lecture we will start our discussion with solving that problem and get some insight out of it. So the problem was, consider a sample of silicon at T equal to 300 Kelvin doped at an impurity concentration of Nd equal to 10 to the power 15 centimeter cube. That means doping concentration with N-type materials is 10 to the power 15 centimeter cube per centimeter cube, and Na is 10 to the power 14. That means the doping concentration of acceptor atoms is 10 to the power 14 per centimeter cube. Assume electron and hole mobilities are given in the table 5.1. It was the table we have discussed in the last lecture. Calculate the drift current density if the applied electric field is E equal to 35 volt per centimeter. So we are asked to determine the J drift. The first task, as you can recall from the equation of J drift, this is the equation of J drift. So we need these values particularly. E is the charge of electron or hole. This is a constant and we know that, so this is not a problem. The next thing we need is N. N is the electron concentration in the material, which is not explicitly given in the question. So the first task is we need to determine this value of N. Mu N is hole mobility. We actually know the hole mobility from the table. I have also suggested you to memorize them if possible. So mu N is not a problem. Then comes P. As I have said for N, P is also a term which is not explicitly given in the question. P is hole concentration. We need to determine it. And then mu P. Mu P is again something we already know from the table or we know from our memory. And then comes the applied electric field E, which is actually given in the question, that is 35 volt per centimeter. So the first task is we need to determine the values of N and P. Back to the problem. So in this case, you can see obviously Nd is greater than Na. That means in the silicon slab, the concentration of donor atom is higher than the concentration of acceptor atom. That means essentially this silicon is an N-type silicon. We have already gathered some formula from the previous lectures, from previous topics. This is one formula we have learned in our previous section. This is actually N means the whole concentration in the extrinsic semiconductor material. We already know what is Nd and Na. And there is another term involved here, that is Ni. Ni is the intrinsic carrier concentration of a material. This is also a fixed value. You can say there is a typical value of Ni for every material for a certain temperature. There was a table in the 4th chapter of Niemann. In that table you can find that the typical value of Ni at 300 Kelvin temperature for silicon is around 1.5 into 10 to the power 10 per centimeter cube. So we already know the values of Nd and Na from the question, and we know Ni also. So by putting these values in this equation, as you can see here, we can determine the value of electron concentration in this extrinsic material. The value is somewhat close to 9 into 10 to the power 14 per centimeter cube. So as we know the value of electron concentration, we can easily determine the value of hole concentration. The formula is hole concentration is equal to the square root of the intrinsic carrier concentration divided by electron concentration. As this is an N-type material, obviously the electron concentration will be much higher than the hole concentration. As you can see here, the electron concentration we have found is in the order of 10 to the power 14, but the hole concentration is much lower than that. It is in order of 10 to the power 5. So the whole concentration is ultimately 2.5 into 10 to the power 5 per centimeter cube. Now as we know the values of N and P, the rest is not a problem. We know the formula of drift current, that is J drift equal to E multiplied by mu N plus mu PP multiplied by E. So J drift is equal to essentially the value of E is 1.6 10 to the power minus 19. Then the typical value of mu n for silicon is 1350. There you go. Multiplied by the derived electron concentration, that is 9 10 to the power 14, plus 480 is the typical value for mu p, and multiplied by the whole concentration, which is 2.5 10 to the power 15, multiplied by the applied electric field 35, and the result is 6.804 ampere per centimeter square. So if you do this correctly in similar fashion, the answer may vary a bit. I asked everyone to practice it in the end of the previous lecture, so if you have done it correctly, kudos. Let's move on to our next discussion. The drift current density was J drift equal to E multiplied by N mu N plus P mu P multiplied by E. This whole term, E multiplied by N mu N plus P mu P, this whole term is incorporated in a single term, that is sigma. So J drift is essentially sigma E, where sigma is obviously this value. This sigma is considered as the conductivity of the semiconductor. You can understand why it is called conductivity with some sort of common sense, because if E is kept fixed, then if we increase this conductivity, our current increases. So if sigma increases, current increases. If sigma decreases, current decreases. So that's why this sigma is referred to as conductivity. It denotes how well a material is as a conductor. So the reciprocal of this sigma, which is rho is equal to 1 by sigma, and obviously sigma is this value, so rho is equal to 1 by E multiplied by N mu N plus P mu P. This rho is denoted as the resistivity. It is the opposite term of conductivity. In the case of conductivity, if E was kept fixed and conductivity was increased, J drift increased. But in terms of resistivity, if E is kept fixed and resistivity is increased, then J drift actually decreases. Let's move on. Consider this figure here. You can see a silicon slab right here. This is a silicon slab, and the measurements of this slab is also given. The cross-sectional area is actually A, and the length of this slab is L, capital L. And you can see that a voltage V is applied across it, and this voltage is causing a current I through the silicon slab. So what is the current density? Current density is basically the current divided by unit area. So J, or current density, is I by A, and electric field is applied voltage per unit length. So E is equal to V by L. No problem with that. Now we know from this equation that J drift is equal to sigma E. We are just ignoring the drift term here. Simply we are considering J. J is equal to sigma E. That's fine. Now we want to put the values of J and E here. So J is basically I by A. We know that sigma and rho, these are reciprocal terms. Sigma is conductivity and rho is resistivity. So we have just put the value of sigma in terms of rho here. Sigma is equal to 1 by rho. So there you go. And E is actually V by L. So here you can see that V by L. If we rearrange these terms a bit, then V is equal to, you can see rho goes here, L goes here, and A is in the denominator. So V is equal to rho L by A multiplied by this I here, I. This rho L by A is actually the definition of resistance. You already know from your previous knowledge, lower level courses. Resistance R is equal to resistivity multiplied by the length of the conductor divided by the cross-sectional area. So basically this is nothing but Ohm's law. So moving on, in this section we will talk about some non-ideal effects, some assumptions that we make in our derivation of these equations we have used so far, has some flaws in it, has some limitations, I should say. We will talk a little bit about that. First thing is velocity saturation. This is actually an effect of high electric field. So what was our assumption when we started deriving all this? Our assumption was mobility, or the mu term, is not a function of electric field. So the equation was V drift equal to mu e, if you can remember from the first lecture, mu e. So if mu is not a function of electric field and mu remains constant, then essentially if we increase the applied electric field, our drift velocity should also increase linearly. But there is a limitation to this assumption. We will try to explain it, what is the case if applied electric field is very high. The total velocity of a particle is a sum of the random thermal velocity and the drift velocity. And the random thermal velocity results in thermal energy. We can determine the thermal energy from this equation, half mv square. You already know the formula of this kinetic energy, half mv square, where Vth means the thermal velocity we are referring here. So half mvth square is equal to 3 by 2 kt. K is the Boltzmann constant, and temperature is 300 Kelvin if you assume the room temperature to be 300 Kelvin. We know this value in electron volts, that is 0.0259, and the whole thing results in somewhat 0.03885 electron volts. So this is the mean thermal energy. Now, if the mean thermal energy half m multiplied by V thermal square is this value, we can actually determine the value of Vth or thermal velocity from here. That value is approximately 10 to the power 7 centimeter per second. So in the case of a silicon, in 300 Kelvin temperature, mean thermal velocity is about 10 to the power 7 centimeters per second. We have another type of velocity, that is drift velocity. We can determine the drift velocity using the equation we have already learned. So if in the case of an n-type semiconductor, the electron mobility is 1350 and silicon is not highly doped, it's a low doping concentration in the silicon, then the drift velocity is about 10 to the power 5 centimeter per second approximately, if the electric field is 75 volt per centimeter. So you can see the drift velocity here is 10 to the power 5 and the thermal velocity is 10 to the power 7. That means the drift velocity is just about only 1% of thermal velocity. That means the total velocity of the particle will essentially be almost equal to thermal velocity, and drift velocity will have a negligible contribution to the total velocity. So the applied electric field does not alter the energy of the electron that much. If there is no electric field, the electrons are moving around in the silicon slab in a very non-uniform fashion. When we start to apply electric field, the energy of these electrons starts to increase. Okay, so they keep increasing as you apply more and more electric field. You can say that there is 75 volt per centimeter. So if the energy increases, they starts moving with a greater velocity, and as the energy is increasing higher and higher, the collision between the electrons also increases. So if the collision between the electrons are increasing, then what happens is, after a certain amount of applied electric field, we expect the energy to increase, but as with the increasing energy, the collision between the electrons are also increasing. That means a lot of the energy we have gained through high electric field is used up in these collisions. A great percentage or proportion of this energy is given up in the form of thermal energy while this collision happens. That's why if we increase electric field and the electric field is considerably lower, we can expect the energy of these particles also increase. That's fine. But as we are increasing electric field to a very high level, we will see that the electrons will now actually tend to have more collisions in between them. So a lot of energy we have gained will be used up in those collisions. So the total net energy of these electrons that will contribute to the velocity will remain somewhat constant after a certain level of electric field. The graph is not shown here, but you can see the graph from chapter 5 of the Niemann. You can see that when the electric field is lower, and if the electric field is increased, then the drift velocity is also increasing linearly. But as the applied electric field is greater than 30 kilovolt per centimeter, at that region the drift velocity becomes somewhat constant, because a lot of energy we have gained through this high electric field is used up in these collisions instead of adding to the velocity. So the velocity somewhat becomes saturated. Same things happen for also germanium. In the case of gallium arsenide, the case is a bit tricky, and we're going to explain it here. But instead of saturating, in the case of gallium arsenide, after a certain electric field, the velocity actually starts to decrease. Okay, this was all for this lecture. In the next lecture, we will start talking about our second carrier transport phenomena, that is carrier diffusion. Till then, goodbye.